Hey everyone, welcome back to Real Analysis 1. This will be lecture 12 of the course. And in this section, we're going to finish up our work on topology of the real number line with a super interesting example of a compact set. And that set is called the Cantor set. Let's go ahead and jump into it. We'll call this section 3.3 the Cantor set. So the Cantor set is a very interesting example of a set that's technically a compact set. It just has some very fascinating properties, which we're going to kind of explore a little bit. So let's go ahead and so this Cantor set is named after, if you hadn't guessed, Georg Cantor. Georg Cantor, of course. We talked about him earlier in the course when we got into the diagonalization argument. And specifically the concept of countable versus uncountable. This is all kind of comes from Cantor. So the Cantor set is it's built. It's a set that's built inductively, which means it kind of you start at the base case and you kind of move up and you kind of build this set up iteratively. And so let's go ahead and talk through how the set is constructed. And so we begin with, so the Cantor set is a subset of the closed interval of 0, 1. It is a subset of 0, 1. Okay, so that's where we start. So we're gonna kind of use notation here that I think is pretty good, pretty convenient. And so we're gonna let p0 equal 0, 1, right? And so this is sort of like the first. This is like your starting point. Now what we're gonna do is we're going to iteratively build the Cantor set by removing sections of this interval in a very obviously a very structured way, right? And so from P0, what we want to do is we want to remove the middle third open interval. So we're going to remove the open interval 1/3 to 2/3. Okay. Okay, and so when we do that, you can think of it. So just to make sure that we're very clear on this, right? So you started with 0, 1. And what you're doing is you're removing the middle third. And so what you have left is 1/3. So you're moving from 1/3 up to 2/3 open interval. And so you're left with 0 to 1/3 and 2/3 to 1. All right, so you've got this piece here. Okay, so you've kind of removed this middle third from this interval. Right, and we're going to label these J11 and J12. Right, the first index being like the first iteration, and the second one just telling you which side you're on. Okay. Okay, and so J11. So doing this leaves, so which leaves J11 equal to 0 to 1/3, and J12 equal to 2/3 to 1. Okay, closed. These are closed. All right, and we're going to continue this process. And so from each of these two, so from these two sections, we're going to cut out the middle third again. Okay, so we'll say from each of J11 and J12, we will again remove the middle third. Right, now it turns out when we remove the middle third of this, what we need to remove is 1/3 squared and up to 2/3 squared. All right, so 1/9 up to 2/9. All right, that's what technically the middle third would be here. And then on this side, it's actually 7/3 squared up to 8/3 squared. Right, so that would be this middle section. Right, so kind of trying to draw the same picture here. So I've got what my zeros are here. Okay, this is going to head over to here, and then I've got like 1 there. So what I've done now is I'm removing 1/9 to 2/9, right? And so now this is going to look more like this. Right, so I've got this piece here, and then over here I've got 2/3 up to what, 7/9, and then 8/9 up to 1, right? And so now I've cut this piece out. Right, now notice I'm just like cutting out these thirds each time. Okay. Now the length of these intervals are all the same. They're 1/9. Okay, 1/3 squared. Okay, and so after each iteration, what the contour set is going to be doing is we're going to kind of be building on this cutting out. So the contour set starts with this interval 0, 1, and we successively remove middle thirds in a symmetric way, sort of a fractal way. Okay. Right, and so technically up here we started with P0, then P1 would have been equal to J11 or J12. I forgot to write that. And so here we're at the second iteration. P2 is going to be equal to these 4, which we'll call J21, J22, J23, J24. So P2, after the second iteration, you've got J21 or J22 or J23 or J24. And we're just going to continue on like this, right? We just continue removing and from this interval. Right, and so what I would say is we can continue on like this indefinitely. Right, the numbers get a little difficult, the intervals get a little bit hard to represent, but we're going to continue. We can continue this process indefinitely, such that at the nth step, the union of subsets has a particular form. So at the nth step. The disjoint intervals have length 1/3 to the n. Right here they had 1/3 squared, and then the next one would be 1/3 to the third, and then the nth step would have 1/3 to the n. Right, and then P sub n is very easy to predict. It's just going to be equal to the union from, we'll say j equals 1 up to 2 to the n of j n comma j, right? Where for each j, actually, I'm sorry, let me put this on the next page. We need to have all of this visible at the same time. Okay, so so after the nth step, the length of the removed intervals is 1/3 to the n, right? That's the length of the removed intervals. And P sub n is going to be equal to the union of j equals 1 to 2 to the n of j n comma j. Right? Why is it 2 to the n? Well, because at each step you double the number of intervals. Right? Going back here, the first step we had 2 intervals, the second step we had 4 intervals, the nth step will have 2 to the n intervals. Okay? So this is going to be your P sub n layer, and then we'll say where for each j sub n j is a closed interval, of the form. What does it look like? Well, it's a closed interval, x sub j on top, 3 to the n on the bottom of the lower bound, and then x sub j plus 1 over 3 to the n on the upper bound. Okay. All right, very good. So that's the idea here. Okay, that's the idea. Okay, and so each P sub n is a finite union of closed and bounded intervals, right? All closed intervals are compact, and this is a union of closed intervals, so it is compact, right? So each piece of n is a finite union of closed and bounded intervals, and are therefore compact, we'll say, right? Okay, we remember the theorems from last section, so we know that all of these layers that I'm creating, the union of these layers are compact sets. The other thing to notice, and if you kind of look back at the picture, is that the first P0 contains P1, which contains P2, which contains ... contains Pn, okay, and so on forever by construction, right? Let's look back here. Obviously, if P1 is these two sets, they're contained inside of 0, 1, right? And if P2 is, the union of 1, 2, 3, 4 sets, these 4 are obviously going to be contained in these 2, which are contained in that one, in 0, 1, right? And so there's this nested property of the sets as well. Okay, so what we have here is a finite union. Each of these layers is a finite union of closed and bounded intervals, and therefore compact. And we know that these layers are all nested, right? So these compact sets are all nested, right? So these compact sets are all nested, right? And we know from our previous lecture that means P equal to the intersection of all these, n equals 0 to infinity of P sub n, is a non-empty, right? We know this from the previous theorem, is a non-empty compact subset of 0, 1. Okay. Now this compact subset of 0, 1, this P is called the Cantor set. Okay. All right. Okay. So that's sort of technically how you construct the Cantor set. Okay. So that's kind of technically how you construct it. What I think is really helpful is I think it's helpful if people have a good understanding of what this thing is like visually, because it's a tricky concept. So let me just make a note here along the edge. I'm going to try to draw a decent picture of this thing. I mean, you can't really draw it, but you can draw like the first couple layers and you can extrapolate from that like what's happening. Okay, so layer 1 is P0, right? And it is just from 0 up to 1. So you've got 0 and you've got 1, right? Obviously the number line in the middle here, right? So it's all in there. So you've got the point 0 and you've got the point 1 in P0. Now at P1, what we do is we remove the middle third. Okay, so how many are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll just go over to 9. So we'll put a little something there, and then trying to draw the picture relatively symmetric so it looks good. 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll go to here. That middle third might not be exactly precise, but that's okay. Right, and so then the contour set gets kind of shrunk down. We basically remove this middle section, and so what's in there now are these here. That part's in there. So we've got this point on one end, we got this point on one end, this point, and this point. This is P1. All right, so what do we got here? We got 0, and we've got, what is this, 1/3? And then this is 2/3 up to 1. Okay, so we've got all these points are in P1. Then we move to P2. And what happens at P2? Well, at P2, we remove the middle third from each of these. So we kind of remove this piece and we remove that piece, right? So it looks kind of like this, right? And again, this isn't going to be perfectly symmetric, but you'll forgive me. All right, so it goes like that, and then it goes like that, and then like that, and then like that. Okay, and so I've got this endpoint still there, 0 still there, and 1 is still there. 1 kind of sticks around forever, and so does 0. All right, and then 1/3 we keep again, 2/3 still there. But what happens is in between these two, we cut out a section, right? And so now we've got these intervals, right? And what are the endpoints of those intervals? Well, you've got 0 and then 1/9, and then 2/9 up to 1/3, which would be like 3/9, right? And then over here you've got 2/3, which would be like 6/9, and then up to 7/9. And then between 7/9 and 8/9, that's gone now. And then this would be like, this is 1, so that's like 9/9, right? Okay. Right, so we've got this piece now, and this piece, and this piece, and this piece, right? And that was built up off of this and off of this. Right, and those two are obviously built off the whole thing, right? So I'll just, kind of put this in there just to make sure everybody can see. Okay, right? So we're kind of at each step, we're just shrinking it down, right? And so you can imagine what happens at the next step. Right, now we're going to break these into thirds, right? And so it kind of goes like this and like this. Okay, and then like this and like this. Right, and so you can see how this is going to get really difficult to draw in a moment. Right, so now we've got this part, this part, this part, this part, here, 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 and here. Okay. All right, now again, we've got the 0 and we've got the 1, right? And now we've got all these other pieces. And so this would be 1/3 cubed, so 1/27. And then I'm just going to fill this in. This will be, 1/9 is here. And so that would be like, let's see, 1/3. What that one is. I can't remember that one. So then this one would be 2/9, right? And so, and I won't write them all in. It won't have time. But then you keep this as 1/3. And then this one is 2/3. We still have that one. But now we have these other endpoints, right? Okay, this would be like 7/9 comes back down again, and then 8/9 comes back down. But you got these other ones, right? So you can see all these endpoints. And then of course, so this is P2. Sorry, I forgot to write that. This would be P3, and then P4 would be the same thing. You just break these into thirds, right? And at each step, the number of intervals doubles, right? And the width of the interval goes, decreases by a factor of 3 as well, right? So now, if you think about what happens in the limit, so the question that I would ask is what points are definitely in the contour set? So what points are definitely in the contour set? Right, we can clearly see that like 1/2 is not in the contour set. All right, it was in here and it got thrown out in the first iteration. But one of the points that we know we retained from the first iteration is like 1/3. Right, 1/3 made it through the first iteration. What about like the point that would be right here? Well, it got dumped, right? It got dumped after the second iteration. And the point that's right here got dumped after the third iteration. Which points do we know stick around? Which points never get dumped? Right? Which points never get removed is really the better question. Right? What points are definitely in the contour set? Well, that really boils down to which points never get removed. And what the points that never get removed in the limit are the points that are the end points. The endpoints, right? For example, 1/3. 1/3, it becomes an endpoint of one of the intervals of one of the intervals in the union after the first iteration. And look, it's there in the second iteration, in the third iteration. It's never going away. We're always going to be cutting out the middle third of all of these closed intervals, right? So the endpoints stick around. Same thing here. This 1/27 is never going to get dropped either. We're going to, at the next iteration, we're going to cut out the middle, and then the middle of those two, and then the middle of those four, and so to infinity, right? And so the middle, because we're always taking the middle out, the points that end up sticking around in the contour set, the points in P are the end points, right? Okay, and there are obviously infinitely many of them, but I think we'll be surprised in a moment to find out just how many there are, in fact. It's a little bit, the number of points in P, i.e. the cardinality of P, is a little bit surprising. Okay, so that's the contour set. So this is the contour set, and this is how it's set up, right? So P would include points like 0 and 1, 1/3 and 2/3, right? Just kind of looking up at the list. 1/9 and 2/9, 7/9 and 8/9, etc. There's a lot. I mean, infinitely many, obviously. Right. This obviously this third, finding the middle third of an interval can be done to infinity, right? We know that enough about the real numbers to know that can go on forever. Okay, so this is the contour set, right? And we know from this that there are certain numbers that are just not in the contour set. So, for example, 1/2 is definitely not in P, right? And there are infinitely many others that you could easily find, right? But 1/2 we know gets cut out like right away. It falls out. Okay, very good. So that's the contour set. Hopefully you got a picture in your head at least of how this works, because it's about to get weird. So there are lots and lots of properties of the contour set, and we're just going to kind of go through some of these. So the first property that I'll point out is one that we've already talked about, and that is that P is compact and it's non-empty. Okay, and we kind of saw that already, right? We know because of the way we constructed it that it is a finite union of compact subsets, and so it must be compact. We also know that because it's nested, that and because it's an infinite intersection, it's not empty. Okay, so we've got those two kind of settled already. And what I just said would be like the second property that I would want to point out is that P contains all of the endpoints of the closed intervals. P contains all of the endpoints of the closed intervals, and I'll just write J and K, right? N iterations, each iteration has K subintervals, right? All right. What's the third property? This one is a little surprising, actually, just because of the way it's kind of set up. It's a little surprising. But it turns out that the third property that I would point out is that every point of P is a limit point of P. That's maybe not totally obvious. This one's really simple to prove, actually, so let's kind of prove this. Okay, so we're going to start by just letting P be an arbitrary point inside the contour set. And let's let epsilon greater than 0 be given. Okay. Now what we're going to do is we're going to choose a natural number n. So we're going to choose m, a natural number, such that what? Well, such that 1/3 to the m power is less than the given epsilon, right? So you give me an epsilon, I can go find an m such that 1/3 raised to that power is smaller than epsilon. That's not a problem. We know that. Okay. All right. And so given this, we would say that since P is in P sub m, so the mth iteration, we would say that P is in JMK for some K. Right? So remember those J's, the M here means that we're talking about the mth layer of the Cantor set, and K just means it's one of there's K subsets, right? right? So the second iteration would be, or the first iteration would have two subsets. So J12, we saw that. There's J12 and J11, right? So JMK just means it's one of the K subsets in the mth iteration. Okay. And what does JMK look like? Well, it's a closed interval of this form, x sub k to the divided by 3 to the m. That's the lower end point, and the upper end point is x sub k plus 1 over 3 to the m. Okay. And what's the length of this interval? What's the length? Right? The length is 1 over 3 to the m. Right? So notice that the length, so we'll say length of JMK equals 1 over 3 to the m, and that's less than epsilon, right? Because we've chosen 1 over 3. We've chose this which layer to look at based on the given epsilon. Right? So that's kind of the kicker, right? So that's the thing. So because I can go deep enough in the layering here, I can always find a layer where the subintervals are close enough. They have such a length, or have a short enough length, that it's smaller than any epsilon you give me, basically. And so what that means is that JMK is a subset of the epsilon neighborhood of the point P that is inside of JMK. Right? And so what follows from that then is that both endpoints of JMK will be I'll say it like this, are in P intersect the epsilon neighborhood of P. So this is the contour set. So both of the endpoints of this thing, this guy and this guy, are inside this epsilon neighborhood. Right? And so the definition of a limit point is that no matter how small of an epsilon you give me, I can find another point in the set that is in that epsilon neighborhood. And since there's at least 2 points in this epsilon neighborhood, one of them can't be P. One of these endpoints is not P, therefore P is a limit point. So it's a really beautiful little, really subtle little proof that shows that the Cantor set is comprised of nothing but limit points. Okay, nothing but limit points. Every point in the Cantor set is a limit point. Right? And it's kind of, I guess it's not too hard to believe, but just the way that this is constructed, it feels very discrete. It feels like these points are kind of isolated off when it gets filtered all the way down, but the way that it works, the filtering gets closer and closer and closer, right? And so the width of the subintervals gets smaller and smaller and smaller, right? So that's a very interesting little property. Okay. Now the fourth property worth pointing out is that, so at each iteration we're removing a third of the set, basically. Right, a third of the points in the set are being removed at every iteration. We do this to infinity. And what the fourth property says is that the sum of the lengths of the removed intervals is equal to, what do you think? It's equal to 1. Okay. Right, so just looking back here, the length of the first interval removed was a third. The length of the second interval was 2 times a ninth. The length of the third interval was 3 times 1/27. 6 times 1/27, right, and so on, right? And if we kind of keep accounting for all these intervals that we're removing, and we just keep track of the lengths, when we remove all of them, i.e. when n goes to infinity, the sum of all those lengths equals 1. And this one is really easy to prove, actually. Right, so we kind of said it already. The first interval removed. First interval removed has length 1/3. The second has length 2 times a ninth. Right, you can just go back and just kind of inspect this and see it. Right, the third, what's the third? Well, A third has length 4 times 1 over 27, but I think I'll write 3 to the third instead. This is 2 times 1 over 3 squared, right? So you can see the pattern here, right? And so on. The nth has length, so it'd be 2 to the n minus 1 times the length of each of the intervals is 1 over 3 to the n. We already kind of talked about that, right? So this just points out a nice little, this is just a nice little sum that I can calculate here, right? So the sum looks like this. It'll be the sum from n equals 1 up to infinity of 2 to the n minus 1 over 3 to the n. And I can do some work on this, some really easy work. I can pull a third out, and then it's n equals 1 to infinity of 2 to the n minus 1 over 3 to the n minus 1, right? And so I could write that as 1/3 times the sum, and I'm going to drop, I'm going to index this a little differently so that I can make this 2 to the n, 3 to the n. So I'm going to say n equals 0 up to infinity of 2 to the n over 3 to the n. And so then, of course, that's 1/3 times the sum from n equals 0 to infinity of 2/3 to the n. Right? In this series, we have seen, right, and we know that this is equal to 1/3 times, this would be 1 over 1 minus 2/3, the common ratio. Right? And of course this, what is this? This is 1/3. And then if you do the little bit of math here, you can see this is 3 minus 2 over 3. So it's 1/3 times 1 over 1/3, which is just 1, right? So it's really easy to demonstrate that the sum of these lengths looks like this. All right. Okay. The fifth property, which is kind of obvious somewhat, but you really have to take seriously the idea that you're going to do this to infinity. The fifth property is that P contains no intervals. And this one I won't demonstrate. It requires talking through a ternary expansion, which is just a little bit cumbersome. You can definitely go look this up, though. This is something you can find in lots of textbooks. But basically, like if you think about how we built this thing, this is a little bit counterintuitive because the set is constructed using intervals, right? So you got first 1 interval, then you got 2, then you got 4 intervals, and then you got 8 intervals, and next you'll have 16 intervals. So, but in the limit, there are no intervals. At the limit, every point in the Cantor set is a point with no interval. That's quite, it's just a very interesting property given how you construct the set. But I think if you think about it, you know you're just gonna, the length of those intervals is gonna go to 0, which means you're not talking about an interval anymore, right? So the next property, property 6, is that the Cantor set actually produces all infinite binary numbers. So the Cantor set produces all infinite binary numbers. Now this is kind of easy to see, but it's you gotta have a good picture to work from, right? So for example, and the way I kind of think about it is you're going left or right as you move from P0 to P1 to P2 to P3. As you move down in the diagram, you have to make a choice whether you're going to go left or you're going to go right, right? So if I'm talking about the number 1/3, I start here and I have to go left, right? So I make a left turn to get to 1/3, right? And then I'm here, and then the idea is I'm gonna come up with an infinite strings of lefts and rights. So what do I have to do? I have to go left or right from this interval. Well, from this interval I go right, and then I go right again, and then I stay right, to get to 1/3, right? And so I could represent 1/3 as L, R, 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 and it's always going to be on the right-hand side, isn't it? If you look at the picture, right, left, right, 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 right. It's never gonna. I'm never gonna go left because it's always. This is the most extreme endpoint in layer 1. What about the number 0? Well, with the number 0, I'm going to start by going left, and then I'm going to go left again, and then I'm going to go left again, and I'm just going to continue on left, right? So the number 0 would be like L, 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 dot, dot, dot. Right? I'm always going to go left. What about the number, we'll say 7/9? Well, I start to get to 7/9, I go right, and then I go left, and then I go right, and then I stay right, don't I? So it's right, left, right, right, right to infinity. So that would be 7/9. So right, left, left. Sorry, right, left, right, right. So right, left, right, right to infinity. Right, so you see how these are built up. Basically, you can think of it like I'm going to start at P0, and at each layer I drop down into the contour set. I decide I have to go left or right, and so I just make that decision. 1 would be all L's, wouldn't it? Left, 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 left. Right, and you kind of take some time and like try some of these others. You know, what about 127? Well, it's left, and it's left, and then it's left, and then it's right, right? L, 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 R, R. Left, left. So left, left. Sorry, left, 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 right. I think that's right. Right, and so on. Okay, and so you can probably see that, you know, at each step I'm making a binary choice, and so my choice to use left or right, L or R, could just as well be to use 1s or 0s, right? And so when I see an L, I'm going to put a 0, and when I see an R, I'm going to put a 1, right? So this would be 0, 0, 0, 0. So the first one would be 0, 1, 1, 1. 0 in binary is zeros, all zeros. 7/9 in binary would be 1, 0, 1, 1, 1, all zeros. And then 1, of course, is just, oh, sorry, this should be right. You guys are probably very confused. Would be all 0, all 1s. Right, 1/27 would be 0, 0, 0, 0, 1, and then followed by all 1s. Right, and so you can see, because of the way this is constructed, all infinite binary numbers are going to be on this list somewhere. All infinite binary numbers can be generated using this method. Because, I mean, every time you take a step, you know, each digit is just one layer down, and you have two choices. One layer down, two choices. One layer down, two choices. You can go either way at each layer. And so in this way, you're going to get every combination, aren't you? Okay. And so all infinite repetition binary numbers are going to be in this list, right? Which is just kind of fascinating, right? Given how this set was constructed, it's just fascinating that this aligns and corresponds to just these binary infinite strings. Okay, and so that's the 6th property. The contour set produces all infinite binary numbers. And then the seventh property is that the contour set is actually uncountable. Right, so the Cantor set is uncountable, right? So this is just, I mean, real analysis is full of these things. Obviously, we've seen these before, but this is just kind of bewildering to some extent. You know, you start with the interval 0 to 1, which we know is uncountable. Right, this is an uncountable subset, right? 0 to 1, the interval is uncountable. We've proven that. And I'm going to remove middle thirds I'm going to remove the middle thirds an infinite number of times. right? And I'm going to remove an interval of total width equal to 1, right? So we saw that was what, property 5 or property 4 maybe, right? So we remove all of these middle intervals and or these middle third intervals, and the total length of the intervals that we remove is 1. And yet somehow we're left with P, and yet somehow the cardinality of P is the same as the cardinality of 0, 1. Which means there's the same number of elements in the Cantor set as there are real numbers between 0 and 1. Of course, that's just par for the course with real analysis. They're the same number of numbers between 0 and 1 as there are real numbers in total, right? But now you've removed an infinite number of numbers from this subset, and there's still as many numbers in the Cantor set as there are real numbers in total, right? So the cardinalities are all the same here, uncountable. Right, now, how do we know that P is uncountable? Well, basically, you just kind of look back up here and you say, well, wait a second. I know that this subset, the set of all infinite binary digits is uncountable. And we might have talked about this already. If we didn't, it's very simple to prove this. You can use the Cantor's diagonalization argument. You can use Cantor's diagonalization argument. Right, and I won't do that rigorously here, but just to give you an idea, like the idea is you can, if I try to list all of the infinite, binary numbers, I might have something like, I got 0 here, and then maybe I've got 0, 0, 0, 0, 1 here, right? I can list them in any which way I want, right, and so on. So I come up with some kind of a list, and I know that obviously, one way to do it would just be to kind of list them layer by layer, right? So take the endpoints of each layer and, start there. So I've got 0, and maybe my next one would be 1, and then take the 4 endpoints of layer 1, and then the 8 endpoints of layer 2. You could just list them all, right? You can map them out like that. And so in that way, everything, all of the numbers that you list correspond to a single digit or a single element in the Cantor set, a single number. But it's easy to show that there are numbers that I can't list here, right? Specifically, all I got to do is flip the bit on the diagonal, right? So if the diagonal number is 0, make it a 1. If the diagonal number is 1, make it a 0, right? So my number that I'm not capturing in the list would be something like 1, 1, 1, 0, right? So this number, particularly however it ends, is not on my list, right? And so that's the whole essence of the diagonalization argument. But you could spend a little time and rigorously work this out, but you kind of get the picture, right? You can easily use Cantor's diagonalization to show that this set of numbers here is uncountably infinite, and there's obviously a mapping from the Cantor set to these numbers here, and so these are uncountable. The Cantor set is uncountable, right? And so that is the kind of the key, sort of one of the key items with the Cantor set, right? So you removed all these numbers, and yet you still have retained all of the cardinality of 0, 1. So takeaway here is that the Cantor set is super cool, and there are other properties. We didn't get into the ternary expansion, which is something that's very cool as well, and there are other things that you can find with the Cantor set. But I think we'll leave off there, and when we come back next time, we will start working on limits. So the course is gonna kind of shift gears here, and in the next sections we'll be talking about limits and continuity. So we'll get into limits, and then we'll get into continuous functions, uniform continuity, and then after that we get into the derivatives. right? So we talk about differentiation and what it means rigorously, right? So we've all seen the definition of derivatives, but what's coming up will be a more rigorous treatment. All right, until then, take care.